Okay, well, we've seen asymptotes. We've looked at vertical asymptotes. We've looked at horizontal asymptotes. This is kind of the next step up, the next kind of weird situation with oblique asymptotes. And oblique asymptotes occur when the degree in the numerator is larger than the degree in the denominator. We have the second degree in the numerator, first degree in the denominator. So we will not have horizontal asymptotes, but we'll have an oblique, or in this case, a slant asymptote. You may have heard that before. But the asymptotes, the oblique or the horizontal, somebody questioned this earlier, this is what's happening as x approaches infinity and or x approaching negative infinity. So we could have the graph crossing the horizontal or oblique asymptote kind of in the middle. This is only showing what's happening way out infinity and negative infinity. Okay? Now, to find the oblique asymptote, we go through division. And we'll actually look at a couple different types of division. Long division will work on all of these, but some cases, synthetic division works. And this is one case where synthetic division would work. But let's first go through long division. We have our x squared minus 2x minus 8 divided by x minus 1. Now, what we're thinking about here is kind of the same idea of turning an improper fraction into a mixed number. Hopefully you knew 5/4 is same as 1 1/4, right? 1 1/4, in our notation, we'll have to think of it as 1 plus 1 over 1/4. That idea will work a lot better with these rational functions. Now, what we need to look at is, here's our divisor. What times x minus 1 will give us at least a term of x squared? Well, that's going to be x. So x times quantity x minus 1 will give us x squared minus x. Then in long division, if you remember how to do this, what's the next step? Well, okay, subtract. So we've got to subtract. Now the problem here is it's not just a single number like we're used to with the 5 divided by 4. We're subtracting this quantity, and this is usually where mistakes are made. What I have to do to remind myself to subtract, multiply that negative through the parentheses. Subtracting a negative x will actually turn that into plus x. Now in this first part, x squared minus x squared, that goes to 0. That should always go to 0. That's why we chose the x to begin with. So, and then negative 2x plus x will leave negative 1x. Okay. Then next step would be what? Okay, bring down the negative 8 and do it one more time. What times the x minus 1 will give us at least the negative x? So we'll multiply by negative 1. Negative 1 times x minus 1. Negative x minus, negative x plus 1. But then we have to subtract, change that to plus x, and then minus 1. Negative x plus x would be 0x. Negative 8 minus 1 would be negative 9. What's the negative 9 represent? Okay, the remainder. That's like what we would do with 5 divided by 4. We'd get 1 as a remainder. So the form here, what we're showing is that x squared minus 2x minus 8, all divided by x minus 1, is the same as our quotient plus our remainder. Now, we'll write it as minus, plus a negative 9 would be minus 9 over the divisor. Now, this is a coincidence. This turned out to be x minus 1, and our divisor was x minus 1. Total coincidence. That nothing related there, just the way it turns out. But our original function, we have changed the form, but this is the exact same function. Okay. Now, the idea on our asymptote, what happens as x approaches infinity for, well, this, well, it's going to be a lot easier to look at it like this. As x approaches infinity, the fraction term goes to what? 0. And, well, technically, as x approaches infinity, x minus 1 will go to infinity. So our limit would be infinity. But the idea here is this is showing it goes to infinity in the form of the linear equation y equals x minus 1. The oblique asymptote will be the equation y equals whatever this part is, because the fractional part will always go to 0, no matter what our original function looks like. If we're dividing, if our numerator has a larger degree than the denominator, the fractional part will go to 0. Okay. Now, also I said we'd go ahead and look at synthetic division to maybe remind you. You've probably seen it, but it may have been a while. So synthetic division, we take the dividend and we just use the coefficients. So 1x squared minus 2x minus 8. And we divide. Now, there's different ways to write this up. You may have seen it a little differently than this, but this is what I do. And then we're dividing by x minus some constant. It has to be in the form of x minus something. We divide by that something. Now notice it's x minus 1. We're dividing by positive 1. If it was x plus 1, to write it in the form we need it, it'd be x minus negative 1. So dividing by x plus 1, we divide by negative 1 synthetically. Okay. So first of all, we bring our first number down, then we start multiplying 1 times 1, and then adding. Negative 2 plus 1, multiply, add. Now, since we've already done the long division, we can kind of see where our results turn out. What's the negative 9? Okay, same as the remainder. A lot of times I will go ahead and kind of box that out, saying it's not with the rest of it. Then the negative 1 would be the constant, and this one would be the coefficient of the x. So the result here, y equals 1x minus 1, and then plus our remainder over our divisor. So we get the same thing. Synthetic division is just a shortcut of the long division. Okay. Now, we do this, find our asymptotes to kind of give us a beginning point for graphing. And we're not going to graph real detailed in this particular section. We'll do that here in a little bit. But first of all, with our function, whether we look at it in this form or this form, do we have any vertical asymptotes? Okay. That would be what? Okay, from the denominator, either there or there, we'd have a vertical asymptote at x equals 1. That doesn't change whether we have horizontal asymptotes or oblique asymptotes. Vertical asymptote, we find that the same way. Now, to show the oblique asymptote then, well, we can graph the line y equals mx plus b. So our y-intercept would be at 0, -1. Now we don't really want to put points here. We want to reserve the points for the actual function. But if you input a little x at 0, -1, what's the slope?
1 over 1.
Okay, 1 over 1, so up 1 and over 1. There would be the next point on our asymptote. And graphing that, we'd have that. So that would kind of give us the basis for the rest of the graph. And then from here you can do what you were doing before. Find your critical points, take your first derivative, set it equal to 0, find where it's increasing and decreasing, find where it's your inflection point, second derivative, set equal to 0, or again where it'd be undefined. So from here on it would be identical to what we've been doing, but you can kind of see where the asymptotes come from. Now, I did go ahead and graph this on a graphing app here on my iPad, and this is the resulting graph. Now you can see, well, I kind of scaled it a little bit differently. Here's 1. You can kind of see, follow the graphing app does not show the asymptote as a dotted line, but you can kind of see that. And then also our oblique asymptote, you kind of see the beginnings of that. Now, really, what we find, we see quite a bit of difference here from maybe about -12 to +12. But if we were to zoom out, those of you that have graphing calculators or some kind of graphing apps, zoom out a bunch of times, and what are you going to see? Well, ultimately, you're going to see just a straight line. Technically, the graph is not that straight line, but I've zoomed out a little bit on this graphing app. This is what we've graphed, except I've rescaled it. Now notice you can just barely see right in here the difference that we were looking at, a little more pronounced difference in our first view of this graph. But you can see the rest of the graph. This is still that graph with the oblique asymptote. But you can see that along this, it looks like a straight line. And that straight line, the graph of the rational function will get closer and closer and closer to the line y equals x minus 1. Now, it will never exactly equal that line, but with our eyes, it sure looks like it does.
So that still has a vertical asymptote?
Yep, that still has a vertical asymptote. This graph, well, you can see the scale here, 128 in the y direction. So we're talking our previous graph, we had a scale, I think I'd had it about 4 instead of 128. So this is just looking way out there. This is looking, well, 128 isn't really approaching infinity, but it's getting pretty close to what would happen at infinity. We could scale it out even farther and it would look almost identical to the equation of the line, y equals x minus 1. But again, the very inside of it, you can barely see just a little bit of curve in there. And that curve, the asymptote, the vertical asymptote, would be at x equals 1. On this scale, it looks like it's right on the y-axis, but technically it's not. Okay? So, I give you the worksheets. I'll let you guys work together on these. Most importantly, find your oblique asymptotes, and then you can go through the derivatives, find your critical points, find your inflection points, and then graph a little bit of detail. You can kind of see where these points come from. Questions?